My name is Lindsey Lack, and I work for Gigamon on the Gigamon Threat Insight team. On that team, I specialize in analytics, which includes developing machine learning models. And this is joint work with John Conwell, and I will be presenting. So the title is Webshell Case Study. This is kind of a boring title, don't you think? I was thinking about what it should be, maybe if it was a clickbait Medium article or something. And so the title I came up with, the alternative title, is 10 Secrets for Creating a Crazy Good Network Detection Model. Do these and you'll put Suricata signature writers out of a job. So first I'll go over some of the motivation for wanting to give this talk, and then a very brief description of what a web shell is for those who may not know. I'll then describe what is needed to implement this type of work. And then I'll cover the specific web shell case study itself. As I go through the case study, I'll highlight the tips and guidelines and principles that we've found to be effective in developing machine learning models for network detection. So if the intersection of computer security and machine learning is both art and science, the content of this presentation is more about the art. So several CAMLIS conferences ago, there was a reflection at the end of the conference, I think Hiram gave it, that the suitable theme for the event would have been malware. This was because so much of the research revolved around the Ember dataset, which had been recently released. After Ember came Ember 2 and then Sorrel. Much of the research around malware has used supervised learning techniques, perhaps because some of the attributes of these datasets that make the approach appealing. There are a tremendous number of samples. The samples are labeled. The samples are easy to define because they're files. Also, because the samples are easy to define, there's a consistency between the samples that would be found in the wild and the samples in the training data sets. Research for network detection has had a much different flavor. The grandfather of network data sets was the 1998 DARPA intrusion detection data set, which was a synthesized data set. Due to privacy concerns, many of the network data sets are less than ideal. They're synthesized, they're created using clever techniques such as honeypots. Sometimes the information's removed. Another complication is that there are various approaches to representing network data: bidirectional flows, unidirectional flows, packets, other custom representations. A regular refrain in the area of network detection research is that the data sets that are available do not adequately reflect what is actually seen on live networks. Overwhelming anomaly detection has been the preferred approach, with labels, if they're available, being used for evaluation rather than training. Sorry. Relative to this discussion about, so the intent of this talk is not to propose a new kind of network data set. The purpose of this case study is to describe what has worked for us in attempting to develop production-appropriate network detection models. Relative to this discussion about research history, two factors seem important to our approach. First is the creation of a custom network data set, which includes things like the use of real background traffic, with emulated malicious traffic, the use of higher level information like that provided by Zeek, and careful selection of the objects under consideration. Second is the use of a supervised approach. Now, neither of these things like the overlay of malicious traffic on background traffic or the supervised learning, they're not themselves novel, but they do seem to be key ingredients to a successful approach. The use of anomaly detection to make sure that unseen attacks can be detected is laudable, but it can be challenging to reduce false positives. I see the sweet spot for a model-based detection as more focused. In this diagram, closer to where the signature approaches are. Signature-based approaches can have a high precision, but focused supervised approaches can also have a high precision and also have some ability to generalize. So a very brief description of what a web shell is. So here on the left, you have a normal user. You have a web server. There's a regular URL that the web server will browse to. And there can be different normal users, and they can be browsing to the web server. An attacker is able to modify the web server. Typically, they will add a new file. It's not the only case, but it's the more typical case. And then that file is available to anybody, but they're the ones that know about it, and they can use it to access their shell. So normally, if an attacker has malicious software installed, the software typically has to act like a client and regularly connect to some outbound server. If the attacker wants quick access to the malware, the polling will need to be more frequent. A web shell, in contrast, leverages the fact that the victim server is already always listening, so no polling needs to be done. And to avoid detection, an attacker will typically only connect to the web shell when needed to conduct malicious activities. So here's the setup for doing this type of creation of a detection model. So one assumption is that you have real data, enterprise volume of traffic, and that you're at least capturing the north-south traffic. Also, an assumption here is that you have some type of additional metadata being generated, such as that's generated by Zeek. In terms of scoping the problem, it is very useful to limit what you're looking at. So in our case study here, we're limiting it to external sources and internal servers, limiting it to HTTP, and limiting it to a web shell hosted by a new file. So the case of if an attacker is in your network and using a web shell somewhere else, we're not covering that. If the attacker has installed their web shell on an SSL server, we're just looking at HTTP. And there are cases where an attacker can modify an existing web server file, and we're not covering that. So on this effort, we had the luxury of support from the threat intelligence part of our team, who did the upfront research on web shells, selected several web shell families, and manufactured activity in the lab that emulated what attackers might do. So we started with 8 manufactured web shell episodes that they created. There's some examples: Behinder, ASPX Spy, Godzilla, Antsword. They created PCAPs in a lab environment. And then we had the extracted Zeek data. So one of the things you need to do is take that lab data and make it look like it's actually happening on the real network. So up top, you see the emulated traffic from the lab for, in this example, Behinder. And then you see some real traffic on the bottom. So what you have to do is stitch this together to make it look more realistic. You can see the colors. I've used red for the emulation and blue for the normal. So one key, and with malware, it's very easy because it's a file. With network traffic, you have to decide what the object under consideration is going to be. So let's say you take the base case and say, okay, it's just going to be these distinct distinct fields, right? Every time you have a distinct set of fields, that's going to be an object that I'm going to evaluate. Well, there's going to be issues because you have different configurations. There are web shells that don't have a host, so they'll have a null host. You have load balancing. You have multiple domains using the same web server. So having the host and dest IP fields separate are not going to work out well in terms of encapsulating the object you're interested in. What I've decided to do in this case is use connected components to piece together those elements and create a new host and destination IP ID that is used here. And it actually gets a little more complicated. This is an example of Behinder. They actually round robin their user agents. And so you do have some web shells that will have multiple user agents. So the final algorithm I used was this, using connected components for host and dest IP. And then for each of those, using connected components to connect together the user agent and the source IP together and the URI path. And to give you an example of what that looks like, let's say these are your raw logs. Up top, you have the web shell. Down below, you have some regular activity. When you apply this final algorithm, you'll get these as the different objects. In this case, you have 3 objects. This actually makes a large difference. There's almost a 10-fold reduction in the number of objects evaluated, and the object has more. Each object has more information potentially that is aggregated. Another issue that you might deal with is noise. So there might be extra information. Usually you don't have to go looking for noise. You'll see it in your results. You can use heuristic rules to look for scanner type activity. In one case, I used signatures to detect bot user agents. And one of the general principles that is helpful is that when you're using signature-based approaches to develop features, an attacker is going to try to adapt if you're using signature approaches, but for noise, it doesn't matter. So in general, if there are signature-based approaches, I try to use them for the noise. Another note is on hard cuts. Often you can make an expert decision. You can say, hey, if more than 5 source IP addresses go to this one path, I'm going to say, that's not possible, and I'm going to be able to reduce my data set. And so even slightly the unbalance between the malicious and the benign. Of course, if you make a wrong decision, you can have false positives. And as you go through this process of developing this, you can always change your mind. You may make a hard cut and decide later that you want to make it just a feature that the model is going to look at. In this actual example, there was one web shell that actually used a hard code user agent. So I initially had made a hard cut and I turned it back to a soft cut so the model could deal with it. Can I get a time check? Thank you. So Another one of the common ways that I see machine learning approached is when somebody's looking at the object that they're developing features for, they try to think of all the features that they can. And then once they have all those features and they've created all those features, they run the model. One thing that I've found very helpful is if you think about the way a decision tree works, often if you see a decision tree printed out, you'll see, the top features at the top of the tree. And often the second layer of features have nothing to do, they're very different than the top feature. So the idea here is kind of think of yourself as a decision tree, make some initial feature decisions of what you think might be good, actually cut the data, and then look at the data and see what stands out between the malicious and the benign that might make good new features. So the second step is the one that's recommended. So we started with these 8 manufactured Webshell episodes, and it turned out that the initial attempts at modeling were actually too good. We were getting, amazing progress, and we thought everything good. Although, I noticed that there was this one feature that was being focused on, and it was always about 4 or 5 was the number that the model was focusing on. And it turned out when the threats were being emulated, they went and they did 4 or 5 actions for each web shell. And so the process that was done to create the emulated content, they were actually doing the same thing each time, and the model was picking up on that. So it's important to have a close relationship between the threat modeling group and the threat emulation group and the modeling group, to make sure that if you have 2 good results, you should actually make the problem harder and diversify your samples. So we ended up ultimately generating 18 episodes, and we increased the variability of the attacker behavior in the additional episodes, making the problem more difficult. And here's an example of some of the strong features some of the strongest features that came out of this research were what I described earlier about the number of things that the attackers do when they interact with the threat model. So you can see here that on the malicious side, these are request sizes and response sizes. So the traffic in the middle means that there was a request of some size, which makes sense because if somebody's interacting with the web shell, they're typically making a decision saying, hey, I want this thing, right? And that might be a different size each time. The first time, maybe they want one thing. The second time, maybe it's down, upload the software. And then the response sizes. So the web shell is giving back different sizes of things. Whereas with the background traffic, you don't see that behavior. So actually, if you look at the purple line on the right in the malicious case, that's a lot of interactions and they're different sizes. And so if you count for a particular sample, the number of different sizes that are there, that's a good feature. So I'm usually biased towards simple models. In this case, we needed to go a little bit more complex. I did end up using support vector machines as a component, which is a little bit simpler model. This is a illustration just of some of the techniques on the left that were tried out. And over on the right, you see the ROC AUC scores. And one important part is I wanted to make sure that I tried different split strategies. So you can see the 18 represents, there's 18 malicious samples. So I did cross-validation. So it was kind of a leave one out type situation for the malicious samples. That should be the easier cross-validation scenario. The more difficult cross-validation scenario is just the split in half. So you have 9 malicious samples and you have to predict the other 9. So you can see here at the bottom, some of the best scoring models. We're down at the bottom, and you can see that there's very little variation in the cross-validation scores. I did try some techniques like SMOTE to try to deal with the unbalanced data, but they actually did worse than the best samples here. So what we actually ended up using was the best of this class. Another note is I did try using AutoML and try to replicate the same strategies that they gave me, and it actually didn't do as well as the other ones that I had found. Ultimately, we ended up using 2 models. One was the best scoring one, and the other was explainable boosting trees. And the usefulness of using explainable boosting trees is when you actually give the results of the detection model to your end users, you can actually explain to them why the model thought that it was interesting. And when you use something like an explainable boosting classifier, you don't need to use the same features. I selected features for the explainable boosting classifier, granted making sure it performed well enough, but that were independent from one another, that had value to the model, but were also easily understandable. One final gratifying technique that was used was the threat emulation team actually held back 2 samples. These were different Webshell families. The original 18 didn't have them included. And after we did the entire process and produced the model was able to successfully find the other 2. So 10 secrets for creating a crazy good network detection model. Overlay emulated malicious traffic over real traffic. Use high-level protocol information like Zeek. Focus your detection scope. Maintain feedback loop between emulation and modeling. Carefully define your object of focus. Remove noise with signatures if needed. Make hard cuts prudently. Be the decision tree. Explain your work and validate outside the process.